the notion of the angle between two arbitrary vectors in this Euclidean space. Namely, we can define cosine phi. Phi is the angle between two vectors u and v. And this vector u and v can be arbitrary vector in Euclidean vector space. Some abstract vector. And we can define cosine angle and this imagined angle between these two vectors as a ratio of the scalar product with vectors u, v, and root square of the scalar square vector u and scalar square of vector v. And we can define the norm of the vector u as the norm is analog of the length of the vector. The square of the norm we can define as the scalar square of this vector. And this formula is the analog of the formula for angle between two vectors in the geometrical vector space. I call cosine phi can be defined using dot product by the following formula. And if we change dot product on the scalar product, we obtain this analog of the formula for the angle between two vectors. But in our abstract case, the angle is not a direct angle. There is some abstract analog of the angle. In such way, we interpret this formula as some number characteristic pair of vectors in the abstract Euclidean vector space. And you can imagine some characteristic which is natural generalization of the angle between two vectors. And using this definition, we can define the notion of the projection of one vector on other. Namely, I recall that for the dot product we have projection one vector v on other vector w as a ratio of the scalar product vw. Scalar. Oh, I'm sorry. It's for dot product. The ratio of dot product vw and the length. The length of the square vector w and the vector w. Namely, this picture illustrates this formula. We have vector w and vector v. What does mean the projection of these vectors on this? We have on the picture the vector A, which is equal to the product of the vector W. We have calculate the length of this projection on this segment is exactly equal the ratio of the scalar product vector VW and divided on the length of the vector W. And with this length we multiply on the unit vector which parallel to the vector W, namely on the ratio W and the length of this vector, we exactly obtain the vector A, which is a projection of the vector V on the vector W. And this formula can be rewritten in the following form. The ratio VW of W squared on the vector W. In this case, I use notation to the vector to the dot product. In this case, we obtain this formula for the geometrical projection. And if we change the dot product on the abstract scalar product, we obtain the following formula for the projection vector V on the vector W. And we can use this formula and obtain the vector which orthogonal vector W. Suppose we have two arbitrary vector W and vector V. And my claim to obtain two orthogonal vector, E1, E2, orthogonal system. We have arbitrary system and our claim to obtain orthogonal system. I can put the first vector of this new orthogonal system E1 is equal first of the vector of initial system E1, let E1 is equal W. And let's construct some vector W which defined by the following two conditions. First condition, this vector belongs to the linear span of the vector W V. And second condition, E1 orthogonal E2 is orthogonal E1 for the scalar product of these vectors is equal to 0. Our claim to obtain such vector E1. We can construct this vector the following way. First of all, we can consider the projection of the vector V on the vector W. And our vector E1 we can define as a difference between V and the projection V on W. Namely, our new vector difference between V and the projection. Easy to see that vector E2 will be orthogonal to the vector W. This assertion we can check by the algebraic way. Namely, we can calculate the scalar product of the vector E2 and E1. Easy to see that vector E2 satisfies to the first condition, because the vector E2 is present as a linear combination of the vector V and vector W. If I rewrite this equality and substitute the expression for the projection, I obtain the following expression: the ratio VW WW multiply on the vector W, and you can see that the vector E2 is a linear combination of the vector V and W. It means that the vector E2 belongs to the linear span of the vector W and V. This condition. And second property too. It means that the vector E2 is orthogonal to the vector E1, which means that the scalar product of these two vectors is equal 0. We can substitute the expression for the vector V in this formula, and we obtain V minus ratio VW multiply W, and E1 is equal W. And after easy calculation using the linearity of the scalar product, we obtain that this expression is equal VW minus WW, and we obtain W minus we obtain that this expression is equal 0, and we check to this property. And the main idea to construct the orthogonal system using this approach. Namely, let's consider this approach in the case when we have three vectors. And after them, we continue this procedure to the arbitrary system of the vectors. Let me have three vectors. U, V, W. And our plan to construct orthogonal system. E1, E2, E3. And we have these vectors U, this vector V, and this vector W. Yeah, I will illustrate the main idea of this algorithm on the example of the three vectors in the geometrical vector space. The main idea following. First of all, you consider two vectors, u and v. And on the first step, we orthogonalize this system of these two vectors. And first step, we put vectors u1 of the new orthogonal system equal the first vector of our initial system u. First step. Second step, we construct the vector e2 which satisfy to the following condition. First condition, e2 belong linear span u v, and second condition, e2 orthogonal e1, or scalar product e2 e1 is equal 0. The main idea, we repeat in this case assertion of the previous example and construct vector e2 as a difference between v and projection of the vector v on the vector u. The same way, easy to check that this vector e2 is satisfies these two conditions. And third step, we construct the vector e1 is equal u, e2 is the vector which belongs to the linear span of the vector u and v, and this vector orthogonal to the vector e1. And we construct the vector e3. We will construct this vector using the following formula. We define this vector as a difference between last vector w and the projection of this vector w on the plane generated by the vector u and v, namely this difference between vector w and projection of this vector w on the linear span of the vector u and v. And this projection we can define as the sum projection of the vector e1 and vector e2. And we subtract from the vector w projections of these vectors on the vector e1 and e2. The main idea this construction is that projection of the vector on the linear span of some vectors is equal the sum of these projections of these vectors of vectors generated this linear span. This main idea. And after subtraction, we obtain the following formula. We obtain the following formula for the third vectors. And I try explain using geometrical interpretation of this procedure algorithm of orthogonalization. We consider this algorithm to the three vectors. But we can understand this algorithm using algebraic approach. What means this formula from point of view, from algebraic point of view? The algebraic explanation is following. And we start with system of three vectors, u, maybe v1, v2, v3. And our claim to obtain the orthogonal system e1, e2, and e3. Orthogonal, it means that pairwise scalar product of different vectors of the system is equal to 0. And we obtain the following algorithm. We put e1 is equal v1. The second, we will look for the second vector e2 as a linear combination of the vector v2 and some coefficients lambda 1, 2, e1. We can present this vector as a linear combination. Such presentation means that this vector belongs to the linear span of the vector of the vectors v1 and v2, and we will look for these coefficients such that the scalar product of this vector is equal to 0. And this condition uniquely defines these coefficients. We can see if we consider the scalar product of this vector e2 and e1 and put this scalar product is equal to 0, we obtain the following expression: v2 minus lambda 1, 2, e1 and scalar product e1. And using the properties of scalar product, we obtain the following expression: v2 e1 minus maybe simple with coefficients lambda times e1 is equal 0. And we can express this coefficient lambda as the ratio v2 e1, e1. And easy to see that these vectors exactly is orthogonal to the vector e1. In the same way, we can define the third vector of our future orthogonal system E3 as a difference E3 minus mu1 E1 minus mu2 E2. And such presentation means that this vector E3 belongs to the linear span of the vectors E3, E1, and E2. And the following condition which defines this vector is fulfilled. And the second condition means that this vector E3 orthogonal to the vector E1, and that means this scalar product is equal to 0, and E3 is orthogonal E2. And we have two conditions. If we substitute the vector E1 and E2 is orthogonal by its construction. We construct this vector, and this vector are orthogonal. And if we substitute this expression in this formula, we obtain the following expression: V3 minus mu1 E1 minus mu2 E2 times E1. And using the condition of orthogonality, we obtain the following expression: V3 E1 minus mu1 E1 E1 minus mu2 E2 E1. And this expression is equal to 0 because vectors E2 and E1 are orthogonal. And we obtain that this expression is equal to 0. And from this equality, we obtain that mu1 is equal to the ratio V3 E1 E1 E1. And the same way, we can calculate the other coefficients mu2. The same way, we obtain and easy to see that this expression, the scalar product of the vectors E1 and E2, is equal to 0. And in the same way, we obtain the following expression: V3 E2 minus mu2 times scalar product E2 E2 is equal to 0. And from this equality, we obtain the expression from the other coefficients mu2. This coefficients is equal ratio V3 E2 E2 E2. And we obtain the algebraic approach to calculation of the orthogonal system. And now we can formulate and prove the main theorem. And this theorem is established the algorithm of orthogonalization, which I try to explain before on the some simple examples using two approaches, geometrical and algebraic. And now we can formulate and prove the main theorem about orthogonalization procedure. maybe. Maybe a question. Any question? Do you understand this example and this algorithm on this examples? Now I will formally prove the theorem we established. This will establish this algorithm, but the main idea was explained on these examples. Have you some question about these examples? Do you understand? Okay, let's continue. Theorem. Let V be a finite dimensional vector space our real number field R. Let W be a subspace of vector space V, and let W1, Wm be an orthogonal basis of W. If W is not equal V, then there exist vectors Wm plus 1, Wn, such that W1, M plus 1 W n is an orthogonal basis of V. We have vector space V, and this vector and some subspace W, and if exists some orthogonal basis in capital W, this orthogonal basis we can extend and construct the orthogonal basis of all vector space V. The theorem asserts that such extension of this initial basis exists. proof of this theorem. The method of the proving of this theorem is called Gram-Schmidt algorithm or orthogonalization process. Explain this process before on the example. The idea is the following. First step, we have subspace which generated by the orthogonal system of the vector W1, Wm, and extend this linear space and consider a space Wm plus 1. Each vector Vm plus 1, some vector which is not belong to this vector space. The idea, roughly speaking, the idea is following. We have some linear independent system of vector W1, Wm, and this system is orthogonal system, but now is not important. And we extend the system to the basis in all vector space V. We obtain some basis is the basis of V. And first M vectors are orthogonal, but other vectors is all these vectors form enough arbitrary basis which is not orthogonal, but we have some basis, and after them we will construct step by step the orthogonal basis in all space V. First step is following. We extend our vector space and add to the generated system of the vectors W1, Wm the vector Vm plus 1. And we obtain m plus 1 dimensional vector subspace. And we will construct the new vectors Wm plus 1, which first belong to the Wm plus 1 vector subspace. As words belongs to the linear combination of these vectors. And second condition, these vectors is orthogonal. Any vectors of which generated subspace capital W. Namely, this vectors is orthogonal any vectors wi, where I runs to the labels from 1 to m. And we can construct this vector Wm plus 1 as the difference between Vm plus 1 minus C1 W1 minus Pm Wm. And these coefficients we can calculate using a condition of orthogonality. Namely, we can consider scalar product Wm plus 1 Wi, and I some labels between 1 and m. And this condition, we can substitute this expression on this formula, and we obtain that the difference easy to see. The vectors W I and W J, for J is not equal I, are orthogonal, and its scalar product is equal 0. And we have only one non-zero element, Ci times scalar product scalar square Wy, and we obtain the following expression. From this expression, we can calculate Ci, which is equal the ratio Vm plus 1 Wi and scalar square Wi. So we obtain exact expression for these coefficients. Ci is equal the ratio Vm plus 1 Wi and the scalar square Wi. And we obtain that the vectors W1, Wm, Wm plus 1 form the orthogonal basis in the subspace Wm plus 1. And we obtain the new subspace Wm plus 1, which satisfy the condition of the theorem. And we can repeat this procedure, and after that we obtain the subspace Wm plus 2, and so on. After n minus m steps, we obtain subspace Wn, which which has a dimension which is equal n, and this subspace of our vector space, and therefore this subspace coincides with our vector space V. And so we obtain the orthogonal basis in all vector space V. And the theorem is proved. The theorem is proved. The main step, this main step, procedure which allowed to start with orthogonal basis of some m-dimensional subspace, construct the orthogonal basis in the space which has first contain our space, our initial space, the subspace, and second has orthogonal basis which is extension of initial orthogonal basis. And if you repeat this procedure n minus m times, we obtain the orthogonal basis on the whole vector space V. And the theorem is proved. Any question? Okay. And now we can consider some examples. Construct orthogonal system. Example. Let's we have some vector space V, which is linear span of the vector V1, V2, V3. This subspace of vector space R4. And in this case, the scalar product coincide with dot product. And let V1 has the following form with a collection of the real numbers, this following collection: 1, 1, 0, 1. V2 is collection 1, minus 2, 0, 0. We can consider that this collection as the coordinates of these vectors in the standard initial basis, which vector space R4. And V3 is the following collection: 1, 0, minus 1, 2. And our claim to construct orthogonal basis U1, U2, U3, orthogonal basis of V. Our claim. Solution of this problem. The solution is to apply Gram-Schmidt orthogonalization algorithm to this system, of these vectors V1, V2, V3. And we will apply this algorithm step by step. First vector u1 we define as v1, the first step. And the second vector, v2, we define as the difference, the second vector u2 we define as a difference v2 minus c1 u1. And c1 we define by the formula from the algorithm, Gram-Schmidt algorithm, namely C1 is equal the ratio V2 U2 times that's all, by the following form. We need use this formula. We can apply the method of calculation, and we can calculate this coefficient if we suppose that scalar product is vector u2 and u1 is equal 0. In our example, the scalar product coincides with dot product. And if we apply this condition, we can calculate these coefficients. If we substitute this expression in this formula, we obtain v2 minus c1 u1 times u1 is equal v2 u1 minus c1 u1. And we can express c1 from this formula, and we obtain this expression. And we can see that no need use this formula. We can obtain this formula by such simple calculation. And using this formula, we obtain that coefficient C1 is equal the ratio of the product of the dot product of these vectors, and we obtain 1 times 1 minus 2 times 1 plus 0 plus 0, and we divided on the scalar square on this vector, and scalar square of this vector v1 is equal 3, and we obtain the ratio minus 1, 3, coefficient C1. And now we can calculate the second vector of our orthogonal system. u2 is equal v2 minus c1 u1 is equal v2 has the following coordinates: 1 minus 2 0 0 minus the coefficients c1 is equal the ratio minus 1 3, and u1 is equal v1, and each vector has coordinates 1, 1, 0, 1. And we obtain I'm sorry. And we obtain the following expression. The ratio 4, 3, the first coordinate, the second coordinate minus the ratio 5, 3, 0, 1, 3. We obtain the following coordinates of this vector u1. And third vector, u3, we can calculate as a difference v3 minus d1 e1 minus e2 e2, and we can, using the formula for these coefficients which obtained before, this d1 is coincide with c I for the m which is equal to, and we obtain the following expression. The ratio v 3 e1 divided e1 e1, and d2 is equal I'm sorry, not ey, excuse me, y. v3 u2 u2 and we calculate d1 v3 times u1, we obtain 1 plus 0 plus 0 plus 2 is equal 3. u1 we have checked before, and is equal 3, and d1 is equal 1. d2 v3 times v3 v3 times u2. We can simplify v3 u2 the coordinates for 3 minus 5 3 0 1 the ratio 1 3, and v3 has the coordinates 1 0 minus 1 2, and if you just the dot product u2 and v3 is equal 4 plus 2, 6, and we divide 3, and we obtain this product is equal to, and U2 times U2 16th plus 25 plus 1 divided 9. 42 divided 9. Seven. The ratio 14, 3, and we obtain that D2 is equal to the ratio 3, 7. And we can substitute to this expression the values of these coefficients, and we can calculate the last vector of our orthogonal system. And we obtain that the vector U3 is equal to V3 minus D1, U1 minus D2, U2. V3 has the coordinate 1, 0, minus 1, 2, D1 is equal 1, U1 is equal U1, 1, 1, 0, 1, D2 the ratio 3, 7, and U2 has the coordinates the ratio 4, 3 minus 5, 3, 0, 0, 1, 3. And we can rewrite this expression in the following form: 1, 0 minus 1, 2 minus 1, 1, 0, 1 minus the ratio 4, 7 minus 5, 7, 0, 1, 7. And we obtain the following expression: 0 minus 1 minus 1, 1 plus minus 4, 7 plus 5, 7, 0. And finally we obtain the following: 4, 7 minus 2, 7 minus 1, 6, 7. Finally, we obtain the expression for these vectors. Easy to see that the orthogonal system is invariant under multiplication any vector of any scalar. And we change and consider the orthogonal system, the vectors of this orthogonal system will be only integer coordinates. We can change, for example, this vector on the vector with coordinates 4, -5, 0, 1. And these vectors can be coordinates -4, -2, -7, 6. And we change this system, and our new orthogonal system, we know this orthogonal system by U1 tilde, U2 tilde, U3 tilde, has the following coordinate. U1 tilde is equal, V1 is equal U1, has coordinates 1, 1, 0, 1. U2 has the coordinates 4, -5, 0, 1. 4, -5, 0, 0, 1. And U3 tilde has the coordinates -4, -2, -1, 6. -7, -7, 6, -7, 6. And we can also consider the orthogonal system which consists from the so-called unit vectors. We can change the size of this vector, and we can construct the system which has the coordinates, such coordinates that the length or scalar square of such vector is equal 1. And if we calculate the norm of this vector, norm of this vector, and norm of this vector, the norm is the root square from scalar square. And this vector and easy to see that the scalar square of this vector is equal 3, and norm is equal root square from 3. This vector 16, 25, and is equal root square from 42, and this vector has a length root square from 105. And we can obtain the so-called unit orthogonal system, or the so-called orthonormal basis in the vector space V. And this orthonormal basis has the following form. E1 is equal E1 E2. Easy to see that in this formula we can change UI tilde on U1. U2 tilde on U2 and so on. And this norm. This ratio will be constant for any normalization of this vector. And we obtain that U1 is equal to the ratio 1 root square 3, and the second vector E2 is equal and the third vector easy to check that we obtain orthogonal system. Easy to calculate the pairwise scalar product or dot product of this vector, and easy to see that these dot products are equal 0. If you calculate dot product U1 and U2, easy to see 4 minus 5 plus 1 is equal 0. This one and this one, minus 4 minus 2 minus 6 plus 6 is equal 0. And this one, minus 16 plus 10 plus 6 is equal 0 also. Actually, we obtain the orthogonal system, this vector, from the orthogonal system, and these vectors form so-called orthonormal system or orthonormal basis in this initial vector space. Any question about this example? Do you understand this calculation which illustrate the before proved theorem? We apply the orthogonalization procedure by Gram-Schmidt to this partial example. Okay, I have 5 minutes. 5 minutes еще? 5 minutes. Okay. Maybe I'm going to consider one more example. Maybe this example will be as exercise. But in my opinion, such example is very important. One of the important and interesting example, non-trivial example. Example 2. I have time only to formulate the condition of the following problem. We have the space of polynomial with real coefficients, and we have following polynomial f1 is equal t, f2 is equal t square, and f3 is equal t up 3 with 3 degree, and vector space V is linear span of this function, and we can define the scalar product in this vector space by the following formula. find the orthogonal U1, U2, U3 orthogonal east. The first step of solution of this problem is following. U1 is equal F1. U2 is equal F2 minus C1 U1. U3 is equal F3 minus C1 D1. U1 minus D2 U2. And these coefficients can be calculated by using the formula for orthogonalization procedure. But in this formula for calculation, these coefficients, we must use this formula for scalar product, a new formula for scalar product. I have no time to continue, and I finished in this place. Any question about maybe some examples about theorem? Okay, thank you for your attention. Goodbye.